So we're on chapter 13, section 2 of your chemistry book, and we're going to be talking about concentration, temperature, and reaction rate. And in the midst and how these things, concentration and temperature, first of all, affect the reaction rate. So it starts off with, if you have an increased number of vehicles in the highway or number of cars in the bumper car amusement park, you have more cars, you're going to have more chance of a collision. And that's the same thing with molecules. So an increase in the concentration of reacting particles increases the rate of reaction by increasing the number of collisions. So more concentration, more atoms, they're going to collide more often, right? And increase the reaction rate. And then if you have, conversely, have a low concentration rate, not very many cars on the road, you have a less chance of crashing into each other. Same with atoms. And so this gives the example down here and talks about reacting gases. And here they take an example of a mole of hydrogen and oxygen coming forth in the midst of how the more concentrated it is by the higher molar volume, you'll have more chances. Chances of increasing the reaction rate. So in doing that, so the concentration is increased by adding more gas to a mixture. So if you add more gas to a mixture, you have more chance of a reaction. And so this is important. Like here's a picture of it. If you add more oxygen, and here's more oxygen added in this, it's the chance of crashing or having a reaction are going to be more. See how much more a flame there is with more oxygen. Less oxygen here is a smaller flame. So concentration affects the rate of reaction, basically. If reactions are not in the same phase, that means heterogenic, the reaction rate depends on the area of contact. So another thing, so number 2, concentration, but another 2 is the area of contact. What does that mean? So it means if you have a log, and you're going to burn a log and it takes some time to burn that log. Sometimes a log takes a long time to burn. But if you take that log and you turn it into sawdust, bam, the sawdust will just burst into a reaction and huge flame. So basically the same thing with coal. If you take a little bit of coal, and you ignite the coal, or say a lump of coal and ignite it, will burn really slow. But if you take powder, coal powder, boom, that happens in mine sometimes, just blows up. So this happens because the greater surface area. So in a bunch of small sawdust chips, you have lots of area, the area to burn. This increases the area, and the same with the coal dust, much more area for a reaction rate to increase, right? So it has to do with on the other hand, a glowing wooden splint will burst into flames when placed in pure oxygen. That's what we had there. So the more gas is added, the more surface area, the faster the rate of a reaction. So that's kind of common sense, isn't it? So temperature and reaction rate. So it says observed rates of reaction cannot be counted just by the number of collisions and concentration, but now we have the energy of how fast the car's going. That would be the kinetic energy. So if you're going really slow, the kinetic energy, and you just bump a car, there's not going to be very much damage. But if you're going 20 miles per hour, bam, or maybe you're going 50 miles per hour, bam, you could really damage. It's a lot of damage, a lot of energy. So basically, temperature increases the kinetic energy of the molecules, and so they're most likely to bump and collide with each other more often and harder. And that harder bump will bump the next one harder and basically cause more of a reaction rate, chain reaction. So the collisions right here of the molecules, you say 10 to the 9th times per second, that's quite a bit. And well, say you have room temperature undergo 10 to the 31, and then each molecule collides this many times, and it goes as you go. Since most reactions are not that rapid, but anyway, in the midst of this, the more rapid the reaction is, the more collisions you'll have, or the more the reaction rate. So temperature will make the reaction rate go up because it increases the kinetic energy. So a general rule of thumb, and this will be on your test, you need to know, is that for every 10 degrees you rise in temperature. So if you rise temperature to 10 degrees, you're going to double the reaction. Say you rise this temperature to 60 degrees. Well, for every 10 degrees, that's 40 degrees. So the first 10 degrees would be 20 degrees. It would double. The next you take that 20 degrees and you double that. And the next you take that, double that, and double that, so this will be very important to know. Just make sure every 10 degrees you double it. So, and that will double the reaction rate. Apparently, the higher temperature must result in a greater fraction of the collisions being effective to produce products. So basically, you'll produce more products being effective there. So going on, here's that picture of kinetic energy. Again, let's go down here to the activation energy. So let me look at my notes here where we were at. Activation energy is the minimum energy. Let's go down. There's a minimum energy that a molecule must possess if it's to react. So a molecule cannot react unless it has that minimum energy. So this is the minimum energy to activate it, so that it will turn into another thing. To activate this energy is called the activation energy, EA. So, and you'll see. Let's look at 13.4. It says 13.4. See if we can go back to that. Sorry. Right here, with the different temperatures and energy reactions, you see, kinetic energy. So the activation energy, where it's going to basically turn into another product, that chemistry, that activation energy is going to, as it takes temperature. So here we have the fraction of molecules have a certain as activation energy, and minimum energy required for reaction is the activation energy. So that's the minimum energy, so here we have the average kinetic energy, and here we have the kinetic energy. So anyway, these are the energy distributed. The minimum energy required for action is EA, the activation energy. So you need to know that. I think that's about it for this. It's pretty... Okay, that's about it. Let's go answer the questions here. Explain in terms of the collision theory why concentration affects reaction rate. So let's look at that. So basically, in the collision theory, the atoms are colliding more often because there's more of them. In concentrations, higher concentration, there's more atoms, so they're going to react. They're going to react with each other more. They're going to bump into each other more. Explain what activation energy means, and activation energy is basically, let's go back, okay. Likewise, there is also a minimum energy that a molecule must possess if it is to react to do molecular damage. This minimum energy is called the activation energy. So it's when it's going to change into something else. We'll find that in the next section. A pile of starch is difficult to ignite, but starch powder dusted in a flame will burn readily because the starch powder has more surface area to react with, and so it will burn quicker. Okay, I think that's it. So it's a quick chapter. I'm going to do the next one. I don't want to go. I would go into the next one here, but we'll do that in the next video. So.